AnimatLab can also be used for simulating the flow of activity within a single neuron. This can be achieved by dividing the neuron into a number of compartments, where each compartment is represented in the program as a neuron, and then connecting the compartments together by electrical synapses. The electrical synapses simulate the intracellular conductance pathway through the axoplasm. This tutorial will demonstrate a compartmental model of a neuron and show the differences between proximal and distal inhibition. The spatial arrangements of synaptic input sites on the dendritic tree can have profound impacts on the integrative properties of a neuron. In other words, the anatomy of a neuron is an important part of its computational mechanism. Let's begin by creating a project. A copy of this project is located at Program Files, AnimatLab, Tutorials, Neural Networks. Please choose where you want to create this project and then name it Compartmental Model. When you have a new project, add an organism and then open its behavioral editor. Disable displaying of the grid and add a graphical node. Delete its text and set the border drawing color to white. Next, we'll add an image of a neuron. There's a neuron image included in the resource folder under AnimatLab bin. Copy that image to your new project directory and select it. Then set the auto size property to node to image. This will automatically size the node to fit your image. Now let's zoom out so we can see the image clearly. Next, let's add a spiking neuron and call it soma. Change its threshold to -52 millivolts. Accommodation to 0, after hyperpolarizing conductance to 2 microsiemens, and after hyperpolarizing time constant to 7.5 milliseconds. Our compartmental model will consist of a spiking soma with a short 3-compartment dendrite sprouting off of it. Add a non-spiking neuron and call it A. Set its resting potential to be -60 millivolts. Then copy that neuron and paste it. Rename the new neuron B. Copy and paste neuron A again to make neuron C. Now add a new spiking neuron and call it proximal inhibition. Set the accommodation to 0. Copy and paste this neuron and call the new one distal inhibition. Do this again and call this one distal excitation. Now draw a synaptic connection from the soma to A. Select the non-rectifying electrical synapse. Set both the high and low coupling to 4 microsiemens. Now connect A to B and B to C using the same non-rectifying synapse. Next, let's add a spiking nicotinic acetylcholine synapse from the distal excitation neuron to C. Set its conductance to be 5 microsiemens, facilitation to 1, and decay to 10 milliseconds. Then add a hyperpolarizing IPSP synapse from the distal inhibition neuron to C. Set its conductance to 5 and its facilitation to 1. Then add another inhibitory synapse from the proximal inhibition neuron to A. Override its conductance to 3 microsiemens. Add a tonic current stimulus to the distal excitation neuron. Set the start time to 30 milliseconds, end time to 45 milliseconds, and amplitude to 30 nanoamps. Now add a line chart so we can see what's happening in our neuron. Add data columns to view the membrane voltages of our compartmental neuron on one axis, and let the other neurons have their own axis. Set the end time to 100 milliseconds and the collect data interval to 0.2 milliseconds. Now let's run the simulation. The current pulse induces spikes in the distal excitation neuron, and these put EPSPs onto the distal end of the postsynaptic neuron. The EPSPs spread passively down the dendrite and eventually arrive at the soma, where, although they're considerably attenuated, they're still sufficiently large to initiate a spike. Now add a tonic stimulus to the distal inhibition neuron. Set its start time to 20 milliseconds, end time to 60 milliseconds, and amplitude to 30 nanoamps. This time our inhibitory neuron spikes, and it's time to bracket the spikes from the excitatory neuron. Not surprisingly, the IPSPs impinging on the distal dendrite counteract the EPSPs arriving at the same site, and the latter now fail to elicit spikes in the soma compartment. Let's increase the conductance of our excitatory synapse to 100 microsiemens and run the experiment again. The excitatory synapse now causes a much bigger conductance increase in the postsynaptic membrane, So now the EPSPs win against the IPSPs and spikes are once more elicited. Now increase the inhibitory synapse to match. Set its conductance to 100 microsiemens. Now the IPSPs win again. The take-home message here is that when the excitatory and inhibitory inputs arrive in the same region of the dendrite, the EPSPs and IPSPs compete against each other, and the winner depends upon the relative strength. In other words, the inhibition is relative, not absolute. No matter how great the inhibition is, it can always be overcome by even greater excitatory input. Reset the conductance of the inhibitory synapse back to its default value of 5 microsiemens. And then add a tonic stimulus to the proximal inhibition neuron. Disable stimulus 2. Set stimulus 3's start time to 20 milliseconds, end time to 60 milliseconds, and amplitude to 30 nanoamps. The strength of our excitatory synapse is still a whopping 100 microsiemens. In order to block this with distal inhibition, we had to have a matching inhibitory conductance. But when we use a proximal inhibition, we can completely block the excitatory synapse using a minuscule 3 microsiemen connection. The tiny proximal inhibition can completely block the massive distal excitation and prevent spikes from being initiated in the adjacent soma compartment. Now delete the proximal connection and add it back on to the next compartment labeled B. The proximal neuron now fails to block the spikes, so it really is the anatomical location of the synapse that matters, not some obscure property of its conductance. The take-home message here is that a relatively small amount of proximal inhibition can completely prevent distal excitation from causing a spike in the soma, and no amount of increase in the strength of the distal excitation can overcome this inhibition. In other words, proximal inhibition, unlike distal inhibition, can be absolute. So what's going on? To understand this, we have to think about current flow within the postsynaptic neuron. The excitatory input in the distal compartment generates a depolarizing voltage. It's the difference between this voltage and the resting voltage of the soma that causes current to flow from the distal dendrite towards the soma, depolarizing it and perhaps making it spike. The EPSP in the distal dendrite tends to depolarize the membrane potential there towards the excitatory equilibrium potential. But no matter how great the strength of the synapse, the membrane potential never depolarizes beyond the equilibrium potential. This sets an upper limit to the voltage difference between the distal and proximal regions, and therefore there is an upper limit to the amount of current that an EPSP in a distal dendrite can drive towards the soma. Let's move the proximal synapse back to compartment A. And then set the excitatory conductance back to 5 microsiemens. Then disable stimulus 3. Now let's change the soma so that it becomes a non-spiking neuron. Set its threshold voltage to -1 millivolts. Let's run the experiment and vary the strength of the excitatory synapse from 10 to 100 microsiemens and look at how this affects the voltage in the soma. At 10 microsiemens, the voltage in the distal dendrite is -22.6 millivolts, and the voltage in the soma is -46.2 millivolts. At 30 microsiemens, the voltage in the distal dendrite is -15.3 millivolts, and the voltage in the soma is -44 millivolts. At 50 microsiemens, the voltage in the distal dendrite is -13.3 millivolts, and the voltage in the soma is -43.4 millivolts. At 70 microsiemens, the voltage in the distal dendrite is negative 12.4 millivolts, and the voltage in the soma is negative 43.2 millivolts. At 100 microsiemens, the voltage in the distal dendrite is negative 11.7 millivolts, and the voltage in the soma is negative 43 millivolts. We can see from this that the voltage in the dendrite is approaching the equilibrium potential of negative 10 millivolts, and the voltage in the soma is approaching negative 43 millivolts as the strength of the excitatory synapse is increased. Above a certain level, there are no further changes in voltage in either the distal or proximal compartments. This is because at the higher levels of synaptic strength, the voltage in the distal compartment has already come close to the excitatory reversal potential, and therefore it cannot increase and it cannot drive more current towards the soma. Now let's consider what happens if we add distal inhibition to the distal excitation. Set the excitatory synapse strength back to 30 microsiemens. Re-enable stimulus 2 and rerun the simulation. The inhibition pulls the membrane potential of the distal compartment away from the excitatory reversal potential, thus reducing current flow to the soma. However, if more excitation is now applied to the distal compartment, this will push the membrane potential back towards the excitatory reversal potential, and thus counteract the inhibition. This competitive interaction can escalate indefinitely. Additional inhibition pulls the membrane potential away from the excitatory reversal potential, and additional excitation pushes it back again. Now increase the strength of the excitatory synapse to 100 and rerun the experiment. The distal membrane potential once again approaches the excitatory reversal potential, and the original peak in the proximal compartment returns close to its original value. Reset the distal excitatory strength back to 30. And re-enable the proximal inhibition. The proximal inhibition massively attenuates the voltage in the proximal compartment, but it has little effect on the voltage in the distal compartment. Increase the strength of the distal excitation to 100 and run another experiment. There's little increase in the voltage in the distal compartment because it's already close to the excitatory reversal potential. Therefore, the distal compartment can't drive more current towards the proximal compartment, and so the increased distal excitation cannot overcome the proximal inhibition. This sort of site-specific difference in inhibitory effects may be an important mechanism in behavior. One can imagine a situation of behavioral choice, where the decision of whether to activate a particular behavior depends upon the balance of conflicting motivations. For instance, in a simple animal such as a crayfish, hunger may tend to elicit foraging behavior, while high light intensity, and hence increased risk of predation, may tend to inhibit it. In this case, hunger might mediate distal excitation onto a foraging command neuron, while light may mediate distal inhibition onto the same neuron. Whether foraging behavior is activated or not depends upon the balance between these antagonistic inputs. On the other hand, one can also imagine a situation of behavioral necessity. Crayfish molt periodically, which means that they shed their entire exoskeleton, and during this period they're extremely vulnerable. Were the animal to attempt to forage while it was in this state, it would almost certainly have disastrous consequences. Therefore, one might imagine that neurons active during molting may mediate proximal inhibition onto the foraging command neuron, so that no matter how hungry the animal was, it would not start to forage while it was actually in the process of molting. While this particular example is purely hypothetical, a similar mechanism has been proposed by Vu and Krasny to account for relative and absolute inhibition in the crayfish tail flip circuit. This tutorial has shown you how to use AnimatLab to produce compartmental neural models, and how the anatomy of the synaptic connections can have a profound impact on the behavior of the neural system.